particular video, we have a radiation of a certain wavelength, some unknown wavelength, causes electrons with a maximum kinetic energy of 0.68 electron volts to be ejected from a metal surface whose work function is 2.75 eV. So essentially, given this diagram, it's saying, look, the minimum energy needed to get these electrons to start ejecting is 2.75. Okay, but there's some extra. It's telling us that these electrons are ejected and these electrons are moving with a kinetic energy of 0.68 eV. So we know that there's enough energy coming in. As a matter of fact, there's some extra which will be transferred to Ke. So in order to find wavelength, all we have to do is set up this particular function for photoelectric effect. The energy coming in is equal to the kinetic energy of the ejected electrons plus the work function. Okay. So here it tells us quite a bit of information already. It tells us Ke is 0.68. So there's a lot of energy coming in, and the extra is going to Ke. And it tells us that the minimum work function here is 2.75 eV. So let's go ahead and just kick it in. Okay. So in order to find wavelength, I'm just going to go ahead and break up E on the left side in order to get wavelength into the function. So I know that E is equal to HF, F of the incoming photon. I know Ke is given as 0.68 electron volts because the problem said so. The problem also states that the work needed to get these electrons to start moving is 2.75 eV. Okay, so 2.75 eV, here's the minimum needed to get things to get going. But this problem we have enough. As a matter of fact, we have extra, so and all that's going to go into Ke. Well, as you can see here, I don't have wavelength yet. Yeah, part A asks you to find wavelength. But what I can do is I can break frequency up into its speed divided by lambda. Okay, so here's H for Planck's constant. That's 6.63 times 10 negative 34 joules per second. Instead of frequency, I want to break frequency up into wave speed divided by wavelength. Well, the question is looking for wavelength. And I know what V is. V is just the speed of light because we're dealing with, again, light here. Okay, on the right side, 0.68 eV plus 2.75 eV is 3.43 eV. So the only thing really unknown here in this particular problem is lambda, and that's essentially what you're trying to find. So from this step to this step, the only thing different here is that I replace V with the speed of light, so which is 3.0 times 10 to the 8th meters per second. Okay, so I notice here I can just go ahead and just do a little condensation or a simplification. I'm just going to go ahead and multiply H with V, and that is going to give me 1.89 times 10 to the negative 25 joules times meters, because the unit S here and the unit S here is going to cancel out. And lambda is still in the denominator. Well, how do I get lambda by itself? I'm just going to go ahead and multiply both sides by lambda, but at the same time divide both sides by 3.43 eV. So watch my cursor. I'm just going to move lambda up to the right. At the same time, I'm just going to move the 3.43 eV down to the bottom left. All right, so as long as your algebra is solid, it should work out. But once again, if you've seen the other video, the units here doesn't match up. In the numerator, you have joules. On the bottom, you have electron volts. So it's important that you convert things so that units will cancel out. This way you end up with the proper units for wavelength. Okay, so here, I think it's easier to just go ahead and convert EV to joules. So you can set up 3.43 electron volts times, well, for every 1 electron volt, that's equivalent to 1.6 times 10 to the negative 19 joules. So make sure you place these values and the units in the right place. Otherwise, you'll be wasting your time. Okay, so if you multiply 3.43 times 1.6 times 10 to the negative 19 joules, you'll get about 5.488 times 10 to the negative 19 joules. So instead of writing 3.43 eV, I can go ahead and substitute that out, and I can replace that with the value I just got of 5.488 times 10 to the negative 19 joules. As you can see here, joules on the top, joules on the bottom cancels out. It leaves me just with the units of meters. Okay, so therefore, if I simplify this on my calculator, I'll get a value of 3.62 times 10 to the negative 7 meters. So I'll just go ahead and highlight that as an answer. If you want, you can convert this value to nanometers, so it would just be 362 nanometers. Okay. All right. Other than that, I'm just keep it in the meters. Here, part B wants us to find. It said what will, the maximum kinetic energy with which the same radiation ejects electron with another metal whose work function is 2.7 eV. Well, Here in part B, it tells us there is a new metal, right? And this particular metal only requires 2.17 electron volts to get these electrons to start moving. Okay, this is how much I have to overcome. So I can just set up the function again. Right? E equals Ke plus W, right? Except W here is different. In the previous problem, the work function for that particular metal was 2.75. This new metal is less. It's 2.17 eV. So it wants us to find the Ke given the same radiation, but we already know from our previous problem, okay, that the total energy that we found was 3.43 eV, right? That's what the sum of it is. It tells our E is 3.43. So I'm just going to go ahead and plug it in. Here, E is 3.43 eV. I want to subtract that from the work function, which is given as 2.17 eV. So therefore, I'm just going to take the difference, and that will give me my Ke. And because it sets in electron volts, I'm done, right? So how much energy was coming in? 3.43 eV. How do I know that? Because we calculate that in the previous part A. What's the work function? 2.17. So therefore, the leftover energy is 1.26 eV. And that is how fast these electrons are moving with, okay? And that is the answer for part B. All right, I hope that helps. Stay nerdy. Don't be black.